Well, see another question, another example. So through problems, your concept will be become, will more clear. See what is given. Ideal gas is given. Okay, 1 mole 6 dm cube, 27 degrees Celsius, adiabatic, and ideal gas 1 mole 3 dm cube. So from 6 dm cube, it is going to 3 dm cube. So first you have to list what information you have. So V1 is equal to 6 dm cube, 6 dm cube, and V2 is equal to 3 dm cube, 3 dm cube, right? And 1 mole T1 is equal to 300 Kelvin, and T2 is equal to not given. So final state temperature you do not have. Against constant external pressure 15 atm. So P external is given 15 atm, 15 atm. Process is adiabatic, so delta Q is equal to 0, right? Find delta Q, 0, work. So to calculate work in against constant external pressure means which type of process is this, reversible or irreversible? See, in the whole question, there is no mention of this process. Which type of process is this? So all of you are knowing from the beginning of this chapter that if expansion or compression is taking place against constant external pressure, then that is irreversible process. So the process is irreversible. Process is irreversible. Right? So the process is irreversible. Now you have to use the formula. First you have to calculate final temperature, then you can very easily calculate the work involved in that. So delta W is equal to delta E. Delta W is equal to delta E, right? So this is equal to NCV delta T means T2 minus T1, and delta W irreversible is equal to minus P external V2 minus V1, V2 minus V1, right? CV is given? No, not given. So I think you can take the CV because I have taken this question only. So CV is equal to 20.91 joules per Kelvin per mole. CV is equal to here 20.91 joules per Kelvin per mole, right? So this is also given here in the question. So first to calculate this final temperature from here. So see P external, wait, so minus 15 atm, and V2 is given 3 and V1 is given. So V2 is 3 dm cube, 3 dm cube minus 6 dm cube. This is equal to 1 mole multiplied by 20.91. Yes, 20.91 joules per Kelvin per mole and T2 is not given, and T1 is given 300 Kelvin, right? So from this equation, first we have to calculate temperature. So this is for calculation of temperature, final temperature. For calculation of final temperature, right? So see here, minus 3 minus minus plus, so this is 45 minus, and this is minus 3, so 15 3 are 45, so 45 liter, dmq means liter atm. So we can multiply this 101 point what 3 101.3 or 2, we can take joules per liter atm. Is equal to this mole cancel, and joules per Kelvin, 20.91 T2 minus 300 Kelvin, right? So this liter atm, this joules is cancelled. So T2 is equal to you will find what 518 Kelvin, 518 Kelvin, right? So this is T2. So final temperature, now you have final temperature. So now you can calculate work. So delta W is equal to delta E is equal to NCV delta T. So 1 mole into 20.91 joules per Kelvin per mole, and T2 is 518 Kelvin minus 300 Kelvin. So this is equal to 518 minus 300 is equal to 218 multiplied by 20.91. So 4558 joules is equal to 4.558 kilojoules. So delta E is equal to, right, 4.56 or 4.558 kilojoule. And now what is delta H? Delta H is equal to NCP delta T, right? So this is equal to 1 mole, and Cp is equal to R plus Cv. So 8.314 plus 20.91 joules per Kelvin per mole, and delta T is equal to 218 Kelvin. So 2 into 218 Kelvin, right? So this is equal to 6.374 kilojoules, right? So delta H is equal to this. You can calculate very easily. See, all the parameters you have calculated: delta Q, delta W, delta E, and delta H. See here, in both the cases, final volume reversible, initial volume and final volumes are same. See, in both the questions, final volume and initial volume same, but temperature you have found different in reversible and in irreversible. Final temperature, see, in the reversible case, what is the final temperature? 464, and here you have this 518 Kelvin. So you will see what initial generalization I have given you regarding adiabatic reversible and adiabatic irreversible, that is reflected in your question as well, right? Now see, another part of this question I have given here, that we have one more formula for calculation of this delta H. So if the same question we try to do with what this this formula, not with this adiabatic formula. If we want to do with this formula, then how to I mean calculate, and on comparison what we can find. So see, the same question, delta H, calculation of delta H in the above question, by using this equation you have calculated delta H, this delta E 4.58, and by this equation, not with this NCP delta T. If you don't want to use this, if you want to use this formula, see how we have I mean proceed, and what is the answer. Now see, for this you have delta E already, not required, so you should calculate this delta PV. So this is equal to, you can write delta E plus P2 V2 minus P1 V1. This delta PV is equal to, right? So P1 you do not have, P1 you don't have, V1 is equal to 6 dm3, and T1 is equal to 300 Kelvin, and 1 mole. This information you have. Now see, P2 you do not have, V2 you have, V2 is equal to 2 dm3, and T2 is equal to, you have 518 Kelvin, 1 mole. So if you have volume, if you have temperature, and 1 mole, and this is initial state, this is initial state, and this is final state. So in initial and final state, you have temperature, you have volume, you have moles. So by using equation of state, very easily you can use equation of state. See, initial state and final state, no problem. In between, it is difficult to use PV is equal to nRT in adiabatic process. But at initial state and at final state, you can use. All the variables are constant with respect to time, and the behavior of the gas is ideal, so you can use very easily. Don't bother that what formula we use here to calculate the initial pressure and final pressure. So you can use PV is equal to nRT in the initial and final state, but during the process it is difficult for you to use, right? But at any moment of time, if all these variables are constant, so you can use. So at initial state and final state, straightforward up, you can use PV is equal to nRT. So P1 is equal to P1 is equal to nRT1 by V1. So this is equal to 1 mole and 0.0821 liter atm per mole per degree Kelvin, 300 Kelvin divided by 6 liters. So liter, mole, mole, Kelvin, Kelvin cancel. So we have this 4.180, right? Similarly, P2 is equal to nRT2 by V2. So 1 mole 0.0821 liter atm per mole per degree Kelvin, and this time 518 Kelvin by 2 liters. So on solving you will get 14.18 atm, right? So now delta H is equal to, we have calculated delta E 4.56, 4.56, 558 kilojoule plus P2 V2, P2 14.18, V2 2 minus P1 V1 4.18 into 6. So this is equal to, this is liter atm. So 14.18 multiplied by 2, 28.36 minus 4.1 multiplied by 6, 24.6. So 4.558 kilojoule plus 3.76 liter atm multiplied by 101.2 joules by liter atm, right? So 380 plus 380.51. So joules. So this is equal to 4.558 . there is a mistake. Actually, I have taken here 2 dm cube, but this is not 2 dm cube. This is 3 dm cube. So 3 dm cube. So here also this is 3 liters, right? So here this is 3. Now I have made this correction here. I have already corrected. So this is kilojoule plus 1.815 kilojoule. So if you add this, so you will get the same value, 6.37 kilojoules, right? So I will, whether you are calculating this with this formula delta H is equal to delta E plus delta PV, or you are calculating with the help of this formula, both will give you the same result, right? So in this way you can calculate this type of thermodynamic functions if this data is given. So I have given you 2 calculations. One is for reversible adiabatic and another for irreversible adiabatic. Keep in your mind that the main crux is to calculate the final temperature. Formula is same, but you have the different formula for work is same, but final state is different if you are moving reversibly and irreversibly in adiabatic process, right? Now see one more question, and this is one of the very good question you can say of thermodynamics, and be ready for such type of questions in your JEE advance. See, a process is given here. 1 mole of water solid means ice you have at 250 Kelvin and converted into 1 mole of water gas means water vapors at 400 Kelvin. And deliberately I have written here calculate the required energy, right? Here I have not mentioned you have to calculate delta H or delta E, right? Because deliberately I have written this so that you can think that what we are going to calculate here, delta H or delta E. So see, this conversion is under constant pressure or constant volume. So all of you are knowing that all such type of processes are in laboratory. We always perform constant pressure system, always design constant pressure system, not constant volume system. So until or unless it is not mentioned that it is a constant volume system, you have to calculate what constant pressure. So under constant pressure the required energy is calculated as delta H. So basically here you have to calculate delta H for this process. So all of you are knowing, as in the above cases, delta H is equal to, we are knowing that NCP delta T. Here temperature is given, initial final temperature is given, and specific heats of ice, see, ice and gas vapor, both is given. So you can take this directly here and calculate very easy, because see, delta H is equal to NCP delta T. N is given 1 mole, and temperature difference here 400 Kelvin. You have to take this water from this to this, right? And so delta T is given. So dear students, if you are using this type of in this type of question, if you are using this formula directly, your answer is incorrect. You cannot use this formula here until or unless you are not able to design the path. See, this is not the single step process that we simply take the ice and put the heat energy here, or whatever the I mean requirement of heat energy that we will provide, and it will convert into this, and directly we can evaluate. No, if you are doing like this, you are using this formula here, your answer will I mean incorrect, because from this ice to gas there are so many steps involved, and you have to consider those steps in the calculation of energy. This is called path designing. As you see in the calculation of PV work or in other parameters, we are designing the path over PV diagram. Similarly, here also you have to design path. Imagine you have to think scientifically that okay, if we have ice and we are putting I mean if we want to convert this ice into vapor, so if we put energy here, so first this ice which is present at 250 Kelvin, that will convert into what? Liquid first, right? And there is a phase change in between. Solid first, this will go solid to liquid. So from here to this, there are so many steps. So first, see, if you have ice or H2O solid, H2O solid at this 250 Kelvin, so when you put heat here, first this solid will increase its temperature up to 273.15 Kelvin, and this is still H2O solid. So this is one step for this. After that, this will change its phase. After that, this will change its phase, and this will convert into H2O liquid. So this H2O liquid is also at 273.15 Kelvin and 1 atm pressure, normal, right? Normal condition. So this is the second step, right? So this is first step, this is second step. So you have to break this whole change in different steps. Now still if you are providing heat here, this will rise again, this will rise the temperature. So this is the chemistry basically. You have to focus the intermolecular forces, how they were changing when you are providing heat to the system. So now this will change its temperature. So H2O liquid you will get, and up to 100 degrees Celsius means 373 Kelvin, right? Now again this will change its phase. So this will convert into H2O vapor. This is also at 373 Kelvin and 1 atm. Now this water vapor that will heated. So now this temperature again this will rise. Temperature of the system will rise. This is H2O vapor, and it is given how much? 400 Kelvin. 400 Kelvin. 400 Kelvin. So this is called what? Path designing, right? So here uh, I have broken this step in such type of steps. So every time when you are dealing with the chemistry problems, thermodynamics problem, so you have to think scientifically that what is happening inside the beaker and system, and accordingly you can break those processes in thermodynamic steps, and then you can calculate. Now for this step you have different formula to calculate delta H. For this step you have different formula to calculate delta H. I think it is given. See here, latent heat of vaporization. Here delta H is given, directly given, right? And here delta H is given from here. So you have to calculate here, you have to calculate here, you have to calculate here, you have given this, but it might be possible that it is required to convert the units basically. So then you have to add all the, because this is extensive property, you can add or subtract, so you have to add all these, then your answer will be correct. And if you are considering from here to here directly and taking this CP and subtracting your answer, I mean calculating this, your answer will be wrong because you have ignored this step, right? You have ignored this step. You have ignored this step, right? This will work here, right? No problem. This will work here, but this will not work here. This formula will not work here, right? So every time when you have I mean such type of problems, then you have to uh, think scientifically what is happening, how many steps we can design for that complete transformation of matter or in the system, and then add all those I mean steps. So here delta H1, suppose that heat is involved. Here delta H2, although it is given, here delta H3, here delta H4, it is also given, and here delta H5. Then delta H for overall process is equal to delta H1 plus delta H2 plus delta H3 plus delta H4 plus delta H5. And if you are not able to visualize, if you are not able to visualize this, then it is difficult for you to get the correct answer, right? Similarly, if you think that okay, some solid is dissolved in water, so how many steps are there, then accordingly you can design the total heat change involved in that solution making process. So you have to first visualize how this solid dissolves in water and how many steps are there involved in the formation of a solution. Then exactly you can visualize the enthalpy of solution. Otherwise you can I mean you can learn the formula and you can write the definition, but you cannot understand what is happening inside the system, right? So this way we have to calculate this question. So first I am taking this in the heating of this ice from this to this. You see, usually CP and CV, what we are taking, they are independent of temperature. Although this is not correct, but at your level, I will give you the formula, the dependency of CP on temperature, but that formula you should use only when certain constants are given in the question, but that is not I mean in your syllabus. So CP and CV, we assume that they are independent of temperature. So from this heating to this heating, first I am calculating this delta H1. So see, delta H1 is equal to we are moving this heating this ice from here to here, and 1 mole see here 1 mole we are taking. So delta H1 is equal to N Cp of ice and T2 minus T1, T2 minus T1, right? So N is 1 mole and Cp of ice is given 1.925, 1.925 joules per degree or per Kelvin, whatsoever, per Kelvin and per gram. So gram inverse. But here this is given moles. So what to do? This is water. So multiply this with 18 grams per mole, right? And T2 minus T1, 273 minus 250. 273 minus 250 Kelvin. So Kelvin to Kelvin cancel, grams to gram cancel, moles to mole cancel, right? So now we have 1.925 into 18 into 3 2 joules, right? So this is equal to 1.925 into 18 into 23, 796.95 joules, right? Joules. Okay. Now come to the delta H2. So delta H2 is equal to, this is a fusion process. They see conversion of solid to liquid. Whatever heat you are providing to the system, that consumes to overcome the latent heat of fusion. This latent heat of fusion, see here given, it is latent heat of fusion. There is no rise in temperature. So this time delta H2 is equal to basically the energy involved to change the phase. So delta H2 is equal to latent heat of fusion. Latent heat of fusion, and it is given. So this is equal to what is given, 333.51, 333.51 joules per gram, joules per gram, right? So you have to convert into moles. So multiplied by 18 grams per mole. So basically this is also for 1 mole we are taking. So this is joules per mole we can take here. So joules per gram. So this is 18. So what we can write here, 333.51, 333.51 multiplied by 18. So this is 6003.18 joules. Now calculate delta H3. So again you use this formula, delta H3. So so all of you are getting this. This is also joules per mole because we have calculated for 1 mole. So this is here also, this is joules per mole. So this grams cancel. Don't be confused here. This is for 1 mole, right? So delta H3 is equal to again NCP delta T, but this time CP of this liquid. We have to take CP of liquid. So CP of liquid is it is given or not? CP of liquid, it is not given in the question. Specific heat, okay. So specific heat of ice, vapor and liquid. This is equal to, Cp of liquid is equal to 4.184 joules per gram per Kelvin, joules per gram per Kelvin, right? So this time we have to take this Cp of liquid and delta T. So this is 1 mole multiplied by 4.184 joules per gram per Kelvin multiplied by 18 grams per mole multiplied by 373 minus 273 means 100 Kelvin. Delta T is equal to 100 Kelvin. 100 Kelvin. So when we will solve this, we will get 7.53 kilojoules per mole, right? 7.53 kilojoules per mole. Now delta H4, although it is given, but delta H4 is equal to latent heat of vaporization. So this is given in the question, that is 2.257 kilojoules per gram right? So multiplied by 18 grams per mole. So this will come to 40.6 to 6 kilojoules per mole, right? So this is delta H4. Now delta H5, further heating, right? So NCP, this time Cp of vapor you have to take, and delta T. So this is equal to 1 mole, and Cp is given what? 1.996 joules per gram per Kelvin multiplied by 18 grams per mole, and delta T. So 400 minus 373, 400 minus 373. So this is equal to 1.996 multiplied by 18 is equal to this multiplied by 373, 400, so multiplied by 73, so 2622 joules per mole, right? So we can write here 2.622 kilojoules per mole, right? Kilojoules per mole. 1.996 multiplied by 18 multiplied by 73, 2622, so 2.622. Okay, see there is some calculation mistake, so I have corrected this. If 1.996 into 18 multiplied by 27, I have taken this 73, so I mean so this is delta H5. Now this delta H is equal to total Delta H1 796.95 joules per mole, 796. So this is 0.796, 0.796, 0.796 kilojoules, plus delta H2 6003.18. So this is 6.003 kilojoule, 6.003 kilojoules, plus 7.53 kilojoules, plus 40.63 kilojoules, plus 0.97 kilojoule. So this is equal to 55.93 kilojoule. So this is the answer. So if you want to convert 1 gram of ice which is taken at 250 Kelvin, 250 Kelvin, what I have taken, 250 Kelvin, and wanted to convert means 18 gram of water. If you want to convert into 18 gram of water vapors at 400 Kelvin, so you have to put this amount of energy to the system. So if you put this part of this total energy to the system, then 18 gram of water will vaporize and its final temperature is what? 400 Kelvin, right? Got it? So this type of questions you have to first break into the steps, thermodynamic steps, and so for this you have to know what the thermodynamic steps are involved in the conversion of any substance from one state to other state, right? Good. Now see one more question. If you see in this question, what is given? A balloon filled with helium gas, monoatomic gas is this, having pressure 2 atm, right? So initial pressure P1 is equal to 2 atm, right? And T1 is equal to 27 degrees Celsius means 300 Kelvin. What will be the resulting pressure? Resulting, not pressure, resulting temperature if it's burst. So obviously under normal condition it will be kept. So the final pressure will be 1 atm, because whatever pressure is there inside the balloon, after bursting it will disappear, and final pressure whatever we are getting in that surrounding, that will be 1 atm, and T2 is equal to, we have to find out final temperature. See, see, assume that the change occurs reversibly. Although the bursting of tires or bursting of balloon, all they are irreversible process because they are very fast. So that is irreversible process. But here it is given that the changes occurs reversibly. So you have to assume a reversible formula. So very simple, you can calculate this final temperature by using that equation, P1 by P2 to the power gamma minus 1 is equal to T1 by T1 by T2 to the power gamma, and this is monoatomic, so gamma is equal to 5 by 3 for monoatomic gas. Now put P1 2 atm, P2 1 atm, 2 by 1 is equal to gamma minus 1, 5 by 3 minus 1. This is equal to T1 300 Kelvin, 300 by T2 to the power 5 by 3. Right? Solve this, you can take a log on both the sides. So this is 5 minus 3, 2 by 3, 2 by 3 log 2 is equal to 5 by 3 log 300 by T2. So when you solve this, you will get T2 is equal to 227.35. 227.35 Kelvin means minus 45 0.65 degrees Celsius. Right? So obviously there is expansion. So if there is expansion, means loss of temperature in that region you will observe, right? So in this way you can calculate the final temperature. Now see, one question I am giving you as a homework, so all of you should try to solve that question. See, 1 ATM and 0.5 ATM, ten, 20, volume in liters, and here this is pressure, right? This is A, this is B, this is C, A to B, B to C, C to A, right? So calculate W A B C A, right? A B C A. Okay, this is 180. So this is homework. Try to calculate this work involved in this